So good afternoon, everybody. My name is Vinny. I'm a technical advisor at Atlantic Woodworks. We here have Peter. He's going to be the speaker on this webinar today. I'm going to start with his bio. Peter studied marine biology, zoology, and forestry, the University of British Columbia, and he has that science-based foundation as a technical communications specialist to advance a better understanding of wood products in the forest sector. He has more than 30 years experience dealing with regulatory, environmental, sustainability, and operational issues. He is the national super sustainability manager for the Canadian Wood Council, a technical and knowledge transfer organization which provides free technical support to designers, contractors, building and fire officials, owners, and regulators to build a strong wood culture in Canada through education, training, and awareness. In this role, he is developing a training and accreditation program for heavy mass timber and prefabricated wood components installation for trades and general contractors. He regularly presents on achieving great sustainability, durability, and the appropriate use of wood in Asia, Europe, and throughout North America to design professionals, contractors, educators, regulators, and building officials. He is a regular participant and session facilitator with the UN Committee on Forest and the Forest Industry, as well as market reviewer specializing in wood and green economy for the Forest Products Annual Market Review, published by UNECE Forest and Timber Section. He is a member of a Low Carbon Assets Through Life Cycle Assessment initiative of the National Research Council of Canada. So I'm going
to. Okay. So Vinny, that's why I just said, you can just call me old growth in the forest industry, still learning. So thanks everybody for joining, and thank you, Vinny, for presenting this opportunity to me. I think it's a really important topic, and for the wood sector, but also for the construction sector, and also for those who really want to improve the environmental performance and impact of our building. So I'm just going to give you a brief overview of the Canadian Wood Council. We are a technical support organization. We don't charge any funds for any fees for our services. We're here to help people. We're essentially trying to inspire, enable, support, promote, and recognize excellence in wood. And that means that we have to work with people who don't understand it but want to use it. We also work with those who do understand it very well to try and enhance their capabilities and make them their projects the inspiration for those who may want to get into it. So it's an interesting job I have. It's kind of fun, and it's also quite invigorating to see how far we've come in the last 22 years. So what I'm going to talk a little bit today about the mass timber sector, what they are, how they're made, some of the factors that are changing our world of design and construction. I'll show a few typical uses of heavy and mass timber, and then some of the influencers, and then some of the things that I think are maybe opportunities we are not fully aware of. So most of us are familiar about the traditional wood products, the dimension lumber that goes in traditional uses like single-family homes. Those traditional products are also being used in new types of buildings, whether it's low-rise commercial or whether it's mid-rise construction up to six floors. But we also have some new products that have come on the market, especially in the mass and heavy timber area. And these can be used in both traditional uses where light frame or concrete are typically used. And then we have new products, like in this case, wood fiber insulation, that can go into new uses like tall wood. This is a project in the Esquimalt that was designed, and this is a project in Quebec that has been completed, and it's 13 floors. Those are new uses for a new product. So most of us are probably familiar with solid sawn timber or heavy timber. These buildings, we've got a hammer beam design in the cathedral in Europe. And then the projects on the right and the left are construction in Vancouver. If you come out to Vancouver and you go to Gastown Steamworks, you'll see a 9-story building, which is taller than the mid-rise buildings we typically build. And it's a heavy timber, solid Douglas fir columns and beams, and a nail laminated timber floor. So sometimes people say, we don't know how to build with build tall wood. I would argue that we know how to do it. We just forgot that we did. So a little bit about different mass timber products. This is nail laminated timber. That was what I showed in the Steamworks photo. It's essentially dimension lumber that is held in place to adjacent pieces of wood using mechanical fasteners, in this case, metal ones. We call them nails. It's an old style. I've seen it in ice houses in Illinois that were built in the 1800s. It's a very, very strong. It can be used in a single orientation. It's generally supported on both ends. It's not really a good opportunity for cantilever in both directions like some other mass timber products. Glue laminated timber is a heavy and mass timber product. I'm sure you're all familiar with that. One of the great advantages of this is that you can use actually less wood than with a heavy timber product, because the defects in a piece of wood are offset by the wood above or below. So you're basically trapping a defect among solid wood. And this is a way to build up heavy timber elements and getting better use out of smaller pieces of wood. Laminated veneer lumber is a single direction oriented veneer. The veneers are the same as are used in plywood, but they're oriented along the length. So the span is parallel to the orientation of the grain. In plywood, those same veneers and the same resin would be oriented at 90 degrees. Plywood is limited in its size because of that cross lamination of veneers. LVL is a continuous process, and it's done in long billets, continuous billets. Continuous billets are also the process typically for laminated strand lumber, where you take strips, thin strips of wood, use a resin, and produce a long product. Parallel strand lumber, we know it here in Canada as Paralam, was invented in Vancouver, and is the strongest engineered wood product that is commercially available. It takes the same thickness of strips as are used in plywood, and then uses a phenolic resin, and then under pressure and heat, it is extruded into a long billet that is, again, a continuous process, but the billets are typically cut off at 64 feet and then remanufactured into smaller elements. This product can also be glued, as can LVL and LSL. Cross-laminated timber is sort of the poster child for mass timber. It's a fairly simple product that can be versatile in size and thickness. It's just dimension lumber that is machined to have good glue surfaces, oriented at 90 degrees to the layer above or below it, and glued in place under pressure. Sometimes there's side pressure. And it's a really good slab product that can be used in shear applications in walls. It can be used to support gravity loads, and can also be used as a slab or as a floor. And it is typically not used to replace light frame. It's used to displace other materials like concrete, precast or tilt-up concrete. There are a couple of other fairly new products on the market. Dowel laminated timber is the same process as nail laminated timber, but it uses wood dowels, which allows that panel to be machined. There are two manufacturers in Canada, one in Golden, British Columbia, and one in Abbotsford. And when I say machined, I should have mentioned that if you want to create a window or a door opening, you can just cut the piece out and not worry about the nails damaging your cutting edge. And then the other is only made in the United States is mass plywood panels. This is one of the strongest and most stable because it's using an engineered product plywood, and then it's built up into large panels. And this can be used like CLT in either a horizontal slab or as a vertical gravity or shear support. So those are the typical mass and heavy timber products that for which there are increasing opportunities. So here's just a map showing some of the production facilities. There's very little in central Canada, but there's also very little market there. But British Columbia, Quebec are growing. I would like to see a few. I'd like to put a few stars in the Maritimes, but that's an entirely different issue. So there's lots of things that are happening in our design and construction world, and I'm going to talk a little bit about some of those. And these are issues or opportunities for heavy and mass for which mass and heavy timber have solutions. We'll look at, these are the topics that I'll cover. I'll look at regulations. I'll look at the construction sector and some of the issues it's facing, wood product, housing, healthy buildings and design for construction. I'll go through each of these, and I hope you'll start to see why they are sort of interconnected. But we'll start with the international aspect around carbon. Typically, when we talk about wood, we think of it as from a 3S point of view. The forest is a carbon sink, wood can sequester carbon, and wood can substitute for carbon, for more carbon intense products. But it actually needs to start with sustainable forestry. So that's the 4th S. Canada is pretty lucky. We've got lots of forests, and we have lots of well-managed forests. It's not perfect because humans come up with regulations, and humans are expected to implement it, so there's going to be screw-ups. But we have more certified forests than the next 8 countries combined. And I'm sorry, I should put up the 2020 data, but I haven't seen this chart for it yet. But it has changed just a little bit. Interestingly enough, until last year, British Columbia would have been between Russia and the United States. The Canadian Forest Service has developed a carbon budget model, and they use that for reporting total emissions. We've got under COP15 or COP21 and COP26, there were all requirements for countries to report carbon emissions and carbon reductions. So in doing this, the Canadian Forest Service, in trying to calculate our forest emissions, has also looked at what are the best ways to reduce emissions and perhaps try to do some mitigation work. And you can see that there's no single solution. It's not just don't cut down trees, and it's not just cut them all down and use them in buildings. There's a mix. That includes some bioenergy to displace fossil fuels. It doesn't do any good to use bioenergy to displace electrical grid electricity. Designing products that can last longer. That includes structures. Harvest a little less to have better utilization of that forest resource. But the best option was actually a bit of a mix of all of them. So this is a study that came out a couple of years ago, you'll find that the net benefit sometimes involves things that are counterintuitive, like having increased product emissions, but you also end up having various reductions in the total carbon impact of the forest in Canada. So the federal government has a greening government policy. They were early adopters of the Pan-Canadian framework. The Net Zero Ready Energy Code is supposed to be coming out this year. British Columbia has procurement documents. There's international agreements around procurement, all of them to basically come up with a low carbon, sustainable, and climate resilient built environment. So let's look at some of the operational regulations. This is a breakdown of the basically impact of various buildings. And on the graph on the right, and you can see that space heating is about 25%, but there's a whole bunch of other energy uses in a typical structure. And this was for included residential and office structures. So there's a bunch of other energy uses. It's not just space heating. Increasingly, though, we're seeing that the embodied impact of buildings is being both is having attention paid to it, but also being incorporated into regulations, especially in Europe, where most of the countries there have recognized that there is some impact from the embodied emissions associated with construction, and that we need to find ways to reduce that. And one of the best ways to do is to do life cycle analysis, evaluation of materials, whether at the whole building LCA or just focusing on embodied impact. But all of these are designed to decarbonize the built environment from both a performance and an embodied method. Embodied impact is often undervalued, and I'll get into this a little bit down the road when we talk about high performance. But typically, embodied impacts are associated with the materials. When it comes to wood, there are several areas of opportunity. This looks like a complicated graph, but it's not. Sorry. This is a model that was created at the University of Washington, looking at from zero carbon to growth of a forest and then a harvest. And then the wood products would go into longer lived usage over time. But if we just have a conventional forest, a natural forest would have an increase in carbon, and then at some point, more carbon starts to emit from forests than is uptake. Forests are sort of like people. They start off small, they grow quickly, they get tall, and then they get big around the middle, and then they start to die. So while an old forest may have lots of wood there, it has also had lots of trees that have grown and died. So a forest reaches a stasis when it comes to carbon. A way to is to increase that carbon benefit is to start having products that last a long time, typically buildings. So where the forest is a carbon sink, the buildings and the long lived products are sequestered carbon. But the big impact as well is in avoided emissions by using, where you can, materials that are less impacting and to displace those that have a high impact. Now, I should say there's no such thing as a perfect material, and we need to understand the impacts of our materials and need to understand where we can merge them together. As an architect or an engineer, I think it's your obligation to understand the impacts and the benefits and the uses of every material, and more importantly, how to integrate those. And if you do that, you have a much better opportunity to have low impact. So getting back to operational LCA, I mentioned in an early one that the heating and cooling is about 25%. This LCA was done in Australia, and they found that the embodied carbon of over the life cycle of the building was 35%. But when you look at this, you see that 24% of the impact over the life is in heating and cooling, and that is where we put our regulations. We don't have really a lot of regulations around how much energy you can use for hot water, refrigeration, or cooking. So when you consider that which we regulate, the heating and cooling, is about 2/3 of the embodied impact in this particular LCA, it gives you some pause to think, well, maybe we do have to have some understanding of the embodied impact of our material and building design. There was a tool that was developed, excuse me, in Canada for the Quebec government to look at this. What are the impacts of our material choices in construction? The tool is called Gestimat. You can go to gestimat.ca. It's free, and it allows you to input your building design using a typical construction or even a material takeoff for the structural elements. It doesn't include the building envelope. It doesn't include the furnishings, the fixtures and stuff. But what it does look at is actual construction systems that are typically used in the built environment. So for example, if you're looking at a typical steel, open web steel truss, steel deck, rebar, and concrete, the data from CREG would give you would input the quantity of materials, the nature of the material. Is it a 50 MPa? Is it 20 MPa concrete? And it tallies all that up and comes up with a kilogram of CO2 equivalent for each assembly. And then you total up the total assemblies you have in your building, and that gives you your base. So this is what it would look like for steel concrete floor, and this is what it might look for a wood one. So it's got truss plates, got nails, OSB, and softwood lumber, and they have different volumes or different masses, and that gives you a carbon impact. This focuses only on carbon. This is not an LCA tool, it's an LCA compiler, and with an emphasis on carbon. So that's something you can look at and say, oh, if I go with this system, or if I use these kinds of materials, if you're building, say, a 22-story building or a 2-story building, you can look at the different scenarios that you might consider, input that fairly straightforward, and then come up with an impact evaluation. And to be honest, if the systems that you're looking at are within plus or minus 2 or 3%, it's a wash. But if you look at one and go, wow, this system is 26% less than this system, maybe it helps you direct to the kind of choices or systems you can look at. Ultimately, when you combine embodied and longevity and forest, here's what the IPCC said, and have said it 2 or 3 times now in 2007, 13, and 19. Essentially, we have to grow more forest land. We have to increase the growth of plants on that forest land, and we have to use lumber from that increased forest. And that will generate the largest sustained mitigation benefit. This was not just in building materials. This is the way to have the largest sustained mitigation benefit that is controllable by man. We can't necessarily control what the ocean's carbon uptake is, but if we can increase our forest land base and use more sustainably harvested wood, we can start to mitigate that. So let's look at now the impact of performance and embodied. Typically, the embodied impact is between 12 and 20%. Those are the figures the U.S. Green Building Council has chosen or has determined. So in year 0, I've chosen 15% as a middle ground. In year 0, all of the impact associated with that building over its lifespan has been embedded. Those embedded or embodied impacts are done. Can't undo them, they're gone. Over time, as you add operational impacts, year 1, year 5, year 10, if you have an 80-year lifespan for your building, at year 12, the embodied impact for a building that has the operational impact for a building that has a 15% embodied impact are equal. And after that, the operational impact surpasses the embodied, clearly. However, we can't always predict what's going to happen in the future. You may have an exceptionally well-maintained and operated building, which reduces your operational impact. You may also have very poor operational performance. You may change, the land value may change. You decide, hey, I got a 3-story building here and the land value went up. I can sell it and make a lot of money. The building may be perfectly good, but we don't need it anymore. We don't want it anymore. So the future is unpredictable. So that's why I think we have to pay attention to what we're doing today, because those impacts are definable and they're complete. We can't undo those. In fact, some work done out of Quebec by Annie Levasseur has indicated that if we save a ton of carbon today, we don't have to save 4 tons going down the road in 80 years. So just like interest in a retirement plan, you hope that the savings that you gather by putting in $100 a month or $300 a month or whatever will accrue so that you have more money down the road than you put in. And carbon impact and carbon benefit accrue over time because the carbon dioxide in the atmosphere lasts a long time. So looking at energy use and high performance, this is a project. I actually have a completed photo that I was neglected. I'm remiss in not putting in there. This is only a 3-story building on a 24-foot wide lot. It was built in North Vancouver. It's heavy timber, it's mass timber, and it's light frame. The front panels are all light frame, built with at BC Passive House. It is a passive house building, very low energy consumption. The back wall is CLT, and the floor plates are CLT, and you can just see the beams are supported on columns. So it's heavy mass light frame, high performance building with a restaurant and a CLT fire separation. So what is the difference between the embodied impacts of, say, a passive building and the embodied impacts of a conventional building? Conventional building, 15%. Passive house buildings typically have 15% more material. So this would mean it would have a 17 and a bit percent. But then you also have a much lower operational impact. So in year 1, year 5, so you've got all of these impacts, year 30 and year 80. Over time, the embodied impact and the operational impact accumulate. But in this case, the embodied impact remains at 54% compared to 46% operational with high performance. So I think it's important to consider that we need to focus on both performance and embodied if we're really going to make a difference. And this is if the building had been a conventional performing building. It would have been about 3 times the impact total. So other opportunities that are coming about are resulting from both technology and codes. As we increase our understanding of heavy and mass timber, I think we're able to better understand what the wood can do, what different systems can do. This is a picture of Brock Commons, just as it was almost completed construction. It is an 18-story building, 17 stories of wood on 1 story of concrete. The wood portion of the building went up in 9.5 weeks. Everything was prefabricated. But the key thing about this is it was technology and research that allowed the codes to change. Codes don't just change because you've got a lobby group that wants it to change. You have to demonstrate proficiency and capability and competency. And that technology enabled a better understanding of what is possible for wood. And as a result, we're going to be seeing significant code changes, and provinces will adopt at their own pace. But the 2020 National Building Code is going to be a tremendous opportunity for those who want to use heavy mass timber. It will allow buildings up to 12-story. It will be an encapsulated mass timber construction, not exposed wood. That will be adopted or adapted to by each provinces. Quebec has a different allowances for exposed wood than British Columbia does, for example. But look for the codes to change to allow mass timber. And what are these codes based on? For the most part, it's based on a concern over fire. So wood burns, but wood performs very well in a fire. So I think we have to start considering that maybe the term combustibility is not necessarily appropriate, because ultimately everything will burn at a certain temperature or given a certain time. But it's how does the material perform in a fire such that the occupants can get out? Fire code is not there to prevent damage. The fire code is there to allow people to get out. Discussion around wood focuses on the char factor. Here is a sort of a profile of a piece of timber that is exposed to fire. You've got the char layer, which is not supportive. The char base is not considered supportive. Into the pyrolysis zone has nominal support, but then you get into the base and the normal wood. That's what has to be calculated to allow for a 2-hour fire rate. It's how much wood do I need after 2 hours to support the structure? This is a picture of a fire test that was done. This picture here was the demonstration at the Surrey Fire Training Center. It's a heavy and mass timber, dowel laminated timber roof and heavy timber columns. You can see the dowel laminated timber had some charring, but most of the DLT remained solid. This is the glulam column that was burned. Had about 5/8 of charring after an hour and 15 minutes of fairly intense fire. So the codes are going to be based on demonstration of performance capabilities. So we're going to shift gear now and look at a little bit at construction. These panels on the right are from a company called Elk Fertighaus in Austria. They are light frame panels that are completely prefabricated and shipped vertically. They include windows, doors, electrical, some mechanical ventilation, cladding on the outside, gyprock, and even paint on the inside. Mass timber is always prefabricated. This is a school in Vancouver, Bayview Elementary on the left. All of those cuts, the notches, placements for beams and stuff were prefabricated at Kolesnikoff in the Kootenays of British Columbia. It is a mass timber building in its entirety. There are some glulam beams over some of the large spans. On the right is a built-up box beam, which is used in Finland for long spans. In British Columbia, for example, we wouldn't be able to use this above certain heights because of the enclosed spaces, but this was not going to be used. So it's a very efficient way to have a low mass, high strength construction system. This is a passive house building in Whistler. It was a heavy and mass timber building. It went up in a couple of weeks. It was a 3-story building that was supposed to be insulated concrete, but the concrete could not be poured and cured because of the timing. It was in winter, and the owner needed this operational by May. Whistler is a cold place in the winter. Lots of snow, as you can see. This was in late October, and the building went up in 3 weeks and was all prefabricated components. One of the other things that we're dealing with respect to construction capacity is a shortage of trades. Most of you probably know Mike Holmes, but there is a real shortage of qualified trades in our construction sector. In British Columbia alone, 330,000 trades trades jobs are going wanting. And that includes everything from formworks, rebar, electrical, plumbing, mechanical, envelope, you name it. There are trade shortages. And it's not just in BC, it's everywhere. That affects productivity. But productivity in the industry has been fairly low over the last 75 or 80 years. And you can see this is this chart just shows the lack of productivity that has plagued the construction sector. It's not pleasant for them. You look at the gross value added per work, which is another measure of productivity. It's fairly low. Even in some countries, agriculture surpasses the productivity of the construction sector. And here's one which is cumulative, shows that the compound annual growth rate of the construction sector is 16 times less than for agriculture. 0.1% annual growth rate over 73 years, from 1947 to 2010. And it has not increased significantly. So what is this leading to? It means that companies have to become more productive, and that is going to mean off-site construction. It's going to mean prefabricated elements. It's going to mean well-trained trades, understanding how to do their job within the confines of a prefabricated system. That doesn't mean prefabrication has to be boring. Lots of things are prefabricated. What's the analogy that was used at a prefab session that we had here in British Columbia about 3 weeks ago, is you'd never buy a car by having all the parts show up in your driveway and have to assemble it yourself. So buildings are complex systems. Quite often, though, a lot of buildings, especially in the single-family home sector, the raw material shows up, you have to piece it together on site and figure out what to do with whatever you couldn't use. That is going to be changing as we have fewer trades who can do that. So we're going to be moving to prefabrication, mass timber, heavy timber, really, really well suited in those areas. So why is prefabrication an important and good opportunity for wood? We have changes in technology and development. We've got new resins, we've got new software. There's BIM is something which is just sort of becoming a natural part of your world. The wood sector has embraced that as well. We've got direct to machine technologies so that the engineer can transfer the information directly to the machining tool. In this case, this is a CNC machine that is going to be processing a CLT panel. This all increases productivity. It also increases accuracy and installation ease. You can imagine that, that pieces that are really well cut and really well designed are going to be able to go together to create strong, tight, and well-performing structural systems. So, and wood is very well attuned to being processed to very tight tolerances, to a fraction of a millimeter. Other materials, they're either difficult to machine or they can't be machined to those types of tolerances. And this is why it's important to really understand, what do I need in the building and what can this particular material deliver for me? These are a couple of jobs that I saw. I had an opportunity to visit some prefabrication of some mass timber facilities in Finland a few years ago. And I looked at this joint on the left and I thought, I could not imagine cutting that by hand. But this took about 3.5 minutes to produce that joint. The precision and the requirement for precision and the ability to deliver that is a real opportunity for heavy and mass timber, especially as we get to bigger buildings, whether it's taller buildings, whether it's larger span, whether it's higher performing buildings where the wood acts as in a thermal capacity, reducing the amount of insulation. These are all opportunities for heavy and mass timber. I managed to get some shots. This was some of the virtual drawings from the Brock Commons project. Every single structural component, every piece of rebar, every bolt was input into this into the software, and then the building was virtually built. They did it several times just to see what is the best placement of crane positions, of people, what's the order or sequencing of installation. All of those details were done before the building was even started, and that's a real opportunity. These software enhance the ability to use wood. I'm not sure how it is where you live, but increasingly cities are getting denser. In some cities like Vancouver, where the city is constrained on 3 sides by water and 1 side by another municipality. They have no more land, so they have to, if they're going to densify, they have to go up. At the same time, there are expectations on performance that are imposed by the province and by the city, and there's a real demand for affordability. How are we going to do all of that? The densification can lead to affordability because you're not building on single-family lots that are very expensive. But at the same time, we're asking for higher performance and increased affordability. The project on the right is called it's called The Landing. It was a project in Vancouver. It was designed. It's a passive house, used prefabricated wood light frame wall systems, and is designed for both market and affordable rental and market purchase. The Vancouver Affordable Housing Agency is looking increasingly at wood because of its speed of construction, and also there's a sweet spot where it is as it's competitive or more competitive than concrete, depending on the nature of the design. But they're increasingly looking at it as a solution. The building on the right is probably taller than outside of the current realm for the codes because it's on a concrete platform and then 12 stories on top of that. But the building that was on the left, sorry. The building on the right, however, could be an all mass timber building, and that would incorporate social and affordable housing, as well as commercial and mercantile. What are some of the typical uses? In mid-rise construction, it is not uncommon for mass timber elements to be used in the elevator shaft. It reduces the differential of shrinkage between 2 different materials like concrete and wood. It also has some good fire resistance capabilities. It can be pre-manufactured and dropped into place, or it can be site built. So it's very versatile. On the right-hand side is a CLT elevator shaft that I think this was in the Crest building in North Vancouver and was 3 stories high. So it was built as a box and dropped into place with a crane. Now, heavy and mass timber can also be used in hybrid construction. There's several projects now are moving to use light frame construction for the vertical elements, the walls, prefabricated walls, on which they would drop a 4 meter or 3.5 meter by 10 or 12 meter long mass timber element that only needs to be screwed into those vertical elements. It gives you immediate floor space for people. It's a lot less cumbersome than having 2 people install joist hangers and then joists followed by plywood and construction adhesive. It's just it's a very efficient way to get the building up. And this is especially valuable on commercial and projects which are going to be sold or generating revenue. Now, wood also merges well with other materials. Several engineering firms have found that they can increase the speed of construction and reduce costs by incorporating steel posts or steel beams. Depending on the span that they require, perhaps steel is a better option. I think the important thing, this again reinforces that you need to understand what materials can do and what they can't or shouldn't do. There's only one building in Canada that is a single material, and that's an igloo. Every other building has to merge materials. So it's your job as designers and contractors to understand what can be used here and what should be used here. The building on the right was a 9-story mass timber building in a place in Finland. I'm not even going to try to pronounce it. I think it's Fukuoka or something, but it was all prefabricated. Long elements were produced, and it's this building here. It's 3 stories, 3 or 4 stories down the back, depending. There were a series of 4 or 5 buildings. But what was interesting about this building, it's a passive house building, but it also has balconies. How did they get rid of that thermal bridge? These boxes here, there's 1, 2, and 3-story boxes were prefabricated with the windows and balcony elements installed and dropped into place using the dovetail sliding connections like Pitzel or Simpson has them, or Sherpa connectors. That's where the prefabrication capability of wood, the precision, is so important, because there's no tolerance for error when you're dropping in a 1, 2, or 3-story balcony onto a system. It has to be exact replacement. But they do it quite regularly. This is, as I say, this is one of 6 buildings in this complex. High performing, beautiful structure inside, and everything was prefabricated. Mass timber can also be used externally, but strategically. It should not be exposed to weather directly or standing water, but it can be used, and as this was an overhang that was then cladded and protected from water to give a nice soffit look. This is a very large facility in Germany. It was made using heavy timber, using a beech LVL columns and trusses, and then heavy timber as wall systems. And the company, SWG, is manufacturing screws for heavy and mass timber construction. Interestingly, they were going to build this building out of steel, and a junior salesman said, "But we're making connections for wood. Shouldn't we be making it out of wood?" And they chose to, and it was cost competitive. This is a project, the company that built that passive house building in North Vancouver has an office. And I show this, it's not a, an exotic use of CLT, it's simply a staircase. There's no metal connections in it. They're using a glue, a structural glue called TS3 that was developed in Switzerland, that is fire resistant, heat resistant, and virtually invisible. It's now been used in a 4-story building called ON5, designed by Robert Malchuk, which is a CLT building. And we'll be producing a case study on that building in the next little while, following it. And we're having a workshop on that as well in January, which I think is going to be available if you're interested in that kind of construction, a 3 or 4-story mass timber building. I will send Vinny the link to that workshop in the case that it is virtual. But NAKUN has really embraced mass timber, and they're using it throughout their projects. So what's next for mass timber? Well, increasingly we're seeing uses which are not purely structural. I just throw this up, curtain wood. It was a curtain wall system that was proposed for a tall building in Vancouver, which I'll get to. But it's really using mass timber to provide the fire resistance of an external curtain wall in a tall building. Here you can see this is how it's very similar in how it could be attached, similar to the steel curtain walls that were used at Brock Commons. But the question was asked, can we do this in mass timber? Can we do this in light frame? And a group got together to propose this, and they're examining how can we build mass timber systems that can be used as curtain walls. And these curtain walls can be high performance, they're airtight, watertight, and they can be applied to a building of any material, wood, steel, or concrete. So healthy buildings. Increasingly, we're seeing there is evidence around stress reduction, parasympathetic and sympathetic nerves responding to the environment which we're in. If any of you are familiar with Ty Farrell, I would urge you to go to his website called causehealth.org. He's just finished a Master's of Neuroscience in Architecture, who knew, at the University of Venice. And he realizes that buildings affect us, whether we're aware of it or not. The building is going to enhance our health and our well-being and reduce our stress levels, or it's going to increase it. Sort of like driving uphill without brakes. You're either going forward or you're going backward. But we're seeing all sorts of benefits that are coming from exposure to natural material, natural light, water, plants, and the surfaces of the structure. Stone, wood, brick. Those all have stress reduction benefits to us, to our health. There's a couple of projects which have come out that talk about this. Materials Matter. Vinny, I think you can get this online. It's downloadable from naturallywood.com. Take a look at it because it reviews some of the studies that were done around health benefits of exposed materials, and make some suggestions as to opportunities. People like wood. As I say, it's not a perfect material, but it's a darn good material if we understand how and when it can be used and why. Ty has used it for, I guess, Credit Valley it's almost 15 years old. This is a public area, Credit Valley Hospital and Cancer Center. He's used it in schools. We typically see wood exposed in schools because there have been increases in grade point average in the United States. Studies have shown natural light and wood increase the grade point average of students, and by reducing their stress level. Their body is focusing on learning, not on dealing with the external stress, be it acoustic or light or temperature or moisture. Finally, designing for deconstruction. I think there's probably none of you in the room that would not understand what designing for deconstruction or circular economy means. But it's a tremendous opportunity for wood because wood materials are generally fastened mechanically. They're not welded, they're not cured. Yes, there are glues, but with heavy and mass timber, you can recover not just the material, you can recover the function. No one's going to take CLT and turn it back into lumber, but they can use a CLT wall as a wall. Now, there are some guidelines and some standards that have been or are being developed for deconstructibility, for disassembly, and increasingly looking at circular economy. Start to explore that and start thinking, how do we design this building so that we can take it apart and use it somewhere else when the land value goes up and someone wants to sell the land, but the building is perfectly usable? And that there is a conflict between designing for durability and longevity and not recognizing the economics that happen to our land, especially in urban areas. So if we can design those buildings so they can be removed, a 3-story office, maybe move it to an outlying area, a suburban area, and recapture that function. And there are lots of benefits to deconstruction. This is a mass timber student residence building that was designed and then put on an earthquake table in Japan, subjected to an earthquake, dismantled, taken back to Italy, erected, dismantled again, and the components used in a kindergarten. But there's a whole bunch of benefits to deconstruction which really align well with mass timber. Many of the benefits of deconstruction are the same benefits you have with mass timber. So where can mass timber take us? This is a 12-story building in Langford, British Columbia. I was on the roof of this building about a month and a half ago, 2 months ago. They're just putting the final elements. It's an all mass timber building, but they have steel components where they need to have extra shear. So it's a really, this is the penthouse apartments, but they chose it because it was cost effective. This is a fabrication system that has been developed for some projects by BC Housing and Vancouver Housing Authority. The company is called Intelligent City. They take mass timber. They have a robotic system that all of the components, windows, cladding, mechanical connections are installed using a roboticized system. They've got 3 robot staging areas and an assembly area. This is, you can see here, it's a metal clad building, but it's a passive house, and it's pretty cost effective for, especially for buildings which are built in the inner area or infill, where you don't have staging areas where you can do a lot of work on site. It came about from this schematic diagram for a 12-story building in Esquimalt that was almost carbon zero. In fact, when it was being proposed, one of the people on the IPCC saw this and it said that really this kind of building is a triple carbon win on operational energy, avoiding embodied carbon from steel and concrete, and by capturing and storing carbon. So sink, sequester, and then enhance operation. So finally, this is the Canada Earth Power. It was for this building that the curtain wood systems were developed. It's a mass timber structural system with a concrete and steel elevator core, combining the materials to take advantage of their strengths and acknowledging their weaknesses. And as far as designing for durability, wood is often targeted as, oh, it rots, it burns, it's weak. Well, it can be those things if it's not well designed. And if people don't understand the material. This building is 1,300 years old. It's designed in a high seismic zone. It has high winds, high rain, lots of fog, but it's lasted 1,300 years because the designers understood what the building was going to face, and they accommodated that. They recognized what the building would have to endure, so they built in the protective elements for that. Oh, and by the way, this building is deconstructible. In Japan, they typically take these temples apart or and rebuild them. They check to see that components are still valid, and they put it back together. And they do that for 2 reasons: to make sure that the building can last longer, but they also to maintain the craft of the skills of the workers to build these buildings. So several years ago, I was asked, why would I build with wood? And I think the question really shouldn't be why would I build with wood. Here's all of the benefits of wood. It's a carbon sink. It's renewable, recyclable. The forests clean the air, clean the water, provide O2. It avoids carbon. It's strong, lightweight, flexible, diverse, inexpensive, and ubiquitous. So the question perhaps should not be why would I build with wood, but if I'm going to build, if I'm not going to use wood, what am I going to use? So think about where heavy and mass timber can be used. It's got new opportunities. It provides new benefits. It has great versatility, and it requires that you learn a bit. It's not light frame construction. It's not tilt up. It's not precast. It's a different material that requires different skills and different understanding. But it is a way for our future construction to really make a difference. So with that, I will stop sharing. And Vinny, if you've got a couple questions there, do you want to deal with them, or do you want me to read them out?
I can read it out for you. Okay. Just to let everybody know as well, the link for the certificates, for the CE credits, I just put that on the chat. so everybody can have access to that. So the first question here is from Keith. Do tools like Gestimat, Athena, Tally, OneClick include sequestration? Do they account for the non-lumber impacts of forests, such as material left on site, mill waste, etc.?
Okay, so Gestimat, Athena, Tally, OneClick, those are all different tools. Athena and Tally are whole building life cycle analysis tools. OneClick is a tabulator of LCAs. There's also the EC3 calculator, which is a calculator, a tabulator or compiler of EPDs. Gestimat has a carbon focus, does not account for the building envelope. As for whether it accounts for the non-lumber impacts of forestry, such as material left on site and mill waste, the material left on site, I think you're referring to the waste from logging. That is accounted for in NRCan's forest calculations. In many cases, we're better to leave that large woody debris, whether it's stumps and stuff, on site. They decay at different rates. The needles of a conifer tree will decay at a much different rate than a stump or the root system. Biogenic carbon is being worked into LCA tools as we go down the road, so you'll see that. Currently, it's not. With respect to mill waste, sawmills never underestimate the mercenary aspect of a mill or something. If there's something that can be used, they typically will. Mill waste can go into products like paper. It can go into biomass to displace fossil fuel or and avoid conversion to methane. So it really depends on what the material is. As well, in many forested areas, you're not allowed to have a reduction of woody debris below a certain volume per hectare, because otherwise you'd be scraping the site bare. So it's a complicated area, but look to see the impacts of carbon emissions from openings and harvested areas being incorporated into calculations going down the road. There was a large summit we had in April about that. Keith, if you have any questions, specific, you can contact me. My email was pmoonen@cwc.ca.
The second questions here would be from Thomas Emodi, but he said he already explained that in one of the latest examples that he gave. It was
okay.
about well, maybe if you want to
Thomas asked, are there studies of the total differences in energy and carbon performance rather than percentages within one construction system? I think there are. You can look at the absolute. When it comes to energy performance, any building can be designed to have very, very good energy performance. Steel, concrete, brick, straw bale, wood. That's the role of the designer. What is not easily determined is what's the embodied impact of that. That will determine what kind of insulation are you using. If any of you have seen any of Chris Magwood's presentations, the insulation in the building envelope can completely undermine the energy performance because it has a very high carbon footprint. So there's so many factors in the building envelope that affect both the embodied and the operational impact. To be honest, if you can build a building out of light frame timber, it's going to have generally a lower impact than a heavy timber or a mass timber because of the embodied impact of those two products. But if you can't use light wood frame, and you have to use steel or concrete, then the equation differs. Oh, Werner. I'm glad you're here. Werner and I used to work together, Werner Hofstetter. How's the production of mass timber in North America emerging? What are the supply chain timelines? Production in North America is increasing. Globally, by 2025, the production of mass timber is expected to be about 2.5 to 3 million cubic meters. North America, 10 years ago had no manufacturing, and now I think our capacity is close to 250,000 cubic meters between Structurlam, their facilities in the United States. There's a large couple plants in Western United States, 4 of them in North America, in Canada. So it is growing. The supply is not really an issue. You can get supply from Europe. There's many European manufacturers that are able and willing and wanting to ship to North America. And I'm hoping that some of them actually start to produce here using Canadian wood. But the capacity will grow, and it's foreseen to grow. One thing you should keep in mind, and you'll hear a lot of concern from the concrete sector that mass timber is competing and stuff. The total volume of mass timber in 2025, if it was 2.5 million cubic meters, pales in comparison to the estimated 10,000 times larger 2.25 billion cubic meters of concrete. So it's 4 orders of magnitude in volume and 5 orders of magnitude in mass for concrete versus wood. There's a comment here in Nova Scotia, we need to factor in the impact of transporting such components to our site, given we don't have the manufacturing plants here yet. Daryl, that's a good point. In most of the LCAs that I've looked at, the transportation is less than 4 or 5% of the embodied and operational impact. So while it's an issue, it's not as big an issue as we might think, depending on the material. If you're transporting material like concrete or steel long distances, you have the same sort of relative proportion, but the embodied impact of those will remain much higher. And Richard asked a question about the environmental impact of the glue content. Great question. It really depends on the nature of the glue because there's 2 aspects. How is the glue cured and how is it manufactured? Most of these glues, if you're looking at say plywood or glue lamp, it's a couple thousandths of an inch thick. These are not glues like the white glue that I slather on when I'm doing woodworking. These are expensive glues with very tight tolerances in how the wood has to be machined, so that it's very, very flat. And then that glue is basically a very strong binder. So the amount of glue is not high. It is in things like parallel strand lumber and higher with LVL and LSL and those. Each of those do have an EPD that has been around. If you want, you can find the EPDs for those products. I'll send a link to Vinny or maybe send the PDFs to Vinny and then you can get them through him.
Absolutely, yeah. So any more questions, guys? And
there was a question, is the presentation available digitally to share with my staff? I can send a PDF. Some of the photos that I have, I'm permitted to use, but I can't allow them to be used by others. I got permission from architects and engineers and stuff, but I can send a PDF to Vinny that has the presentation. I noticed a spelling mistake, so I'll have to correct that first, but otherwise it will be exactly the same, and I'll send that to Vinny if he can give it to you.
Yeah, and I'll also upload that to our YouTube channel, so the whole presentation will be available there. I'll send everybody the link once I upload it as well, and any other links and PDFs that Peter want to share. So I think we're going to wrap it up for now. We are like 8 minutes after 3. Thank you very much, Peter, and thank you very much for the presence here. See you next time.
Thanks everyone for joining.